Okay, so last time we derived the expression of the velocity and acceleration of a rigid body in 3D space. We were able to, in doing so, let's say, exploit some of the mathematical properties of the transformation matrix. And we also were able eventually to recognize some of the terms that constitute the acceleration of a rigid body, namely the linear, the tangent, the Coriolis, and then we also had the tangent component of the acceleration. And so now what we will do from now on is starting to take into account the inertial properties, always of rigid bodies. So in this sense, we will pass from the kinematic, so the study of motion, to the dynamics of rigid bodies. We will take into account the equilibrium of bodies, of a system of multiple bodies. And in doing so, we will basically introduce also, as I was mentioning last time, a very important concept, which is the concept of constraints. We will discriminate between holonomic and non-holonomic constraint. We'll see what is the difference between them. And we will introduce, as a result, the concept of degrees of freedom, of Lagrangian parameters of motion. And eventually, we will recognize the limitation that are inherent in a Lagrangian formulation of the equations of motion, in particular for what regards all those constraints which are enforced not just on the configuration of the system, but on the motion of the system. Okay? But as they say, first things first. So we will start today with the dynamics of rigid bodies. All right. So typically when we deal with dynamical system, we always use the expression generalized coordinates. So generalized coordinates. So why are they called generalized? Because typically they include quantities which are not homogeneous. So a coordinate can be a position, a coordinate can be a rotation, a coordinate can be an acceleration. So they are not typically homogeneous. So that's why they are called generalized coordinates. And in addition to this, we will see that some of these coordinates typically do not possess an immediately identifiable physical meaning. Okay? What do I mean is that if you take into account Cartesian coordinates, you know immediately what you're talking about. Okay, so you have the position and so on of a body, of a particle, or whatever. When you have a generalized coordinates, you can have basically a coordinate formed by, a group of sub-quantities. Typically can be also non-dimensional, which in result has no, immediate intuitive physical meaning. And this sometimes can be a drawback because you are not able immediately to recognize, to be aware if, for example, the quantities, the values assumed by these generalized coordinates have a sense. They actually make sense or not. Okay, but in any case, if you take into account our now well-known relationship of the position of a rigid body in space, what do we have is three coordinates, R1, R2, and R3, I, for the position, so three parameters for the position of, when I call BI, here what I intend, actually, sorry, let's write it like this, BJ. So this means typically B1, B2, B3. Okay, so I could also write B1, B2, B3. So the triad, okay, of the local of the body. So three parameters for the position. And then, depending on the parameterization, we can either have 3 or 4 parameters for the attitude. For example, in terms of Euler's parameters, here we have theta 0, theta 1, theta 2, and theta 3. Okay? So here, let's say 3/4 parameters for the orientation let's say of the BJ. So the vector of generalized parameters here is the following. Typically, it's denoted with a Q. So for the body height is Qi. Qi equal to, we have R1, R2, R3, and then we have theta 0, all with the I superscript. 1, 2, and 3. Okay? Transposed. Typically, these are column vectors, so theta 3. So like this. So transposed. Okay, so as you can see, as we have already said, the vector includes non-homogeneous quantities from a dimension point of view, and typically is composed of, again, 6 or 7 parameters. Now, if we have a system of multiple bodies, the vector of the generalized parameters for all the bodies of the system will, of course, be the number of bodies times the number of parameters. So, for example, let's consider this system of bodies. This. Okay, so imagine a system of multiple bodies like this. Body 1, body 2, body I. And then there are some links, there are some joints, some connections between them. Okay, so in general, what we can write is that, as it is obvious, for a system of, let's say, n with the subscript b bodies, rigid bodies, we have typically what? 6/7 parameters times, if you want, this is actually really a times signature, and b parameters. Okay? So typically the total vector of the parameters is something written like this. So you have Q1. Let's draw it like this. Q1, then you have Q2, up to QNB transposed. All of these are transposed. Okay. So again, this is a 6/7 times NB times 1 vector. Now, this is in fact the number of parameters that you need to define to completely identify your system. But in general, we do have limitations to the values that these parameters can assume. Because, as I said, there may be connections between them, between the bodies, or some relationship between the body and the surrounding environment, which limit the values that these parameters can assume. And these relationships are typically called constraints. So constraint, what is it, a constraint? A constraint can be basically defined as a dependence between bodies or particles, of course, or between a body / particle and the surrounding environment. Okay? So this is the definition of constraint. Okay, something very important. And since our system of multiple bodies is described by a vector of generalized parameters, typically the constraint will be enforced through what? Equations in terms, which will be built in terms of these parameters. Okay? So if you want, you can definitely say that constraints are informed or come in the form of equations in the Q's. Okay. Okay. As soon as you introduce constraints, you establish a relationship between parameters through these equations, through these equations here. And so eventually you will start to divide your generalized parameters into two categories. Those parameters that you can freely set, and those that will come as a consequence of this set, meaning that you will divide these generalized parameters between independent and dependent parameters. Okay? Because you will be able to set a certain number of generalized coordinates as you want, with the value that you want. And then through this equation, constraints equation, all the others will result as an enforcement of these constraints. Okay? And this is in fact the effect of a constraint, as we said explicitly, we wrote it exactly explicitly on the board. That's to say, creating a relationship between coordinates. This is what a constraint is. So this is the important, let's say, aspect. And you can study like this. So as soon as you introduce constraints equations, let's say you partition between dependent and independent coordinates. Just for the sake of clarity, the term parameter and coordinates most of times are used having the same meaning. Okay, so we can talk about generalized parameter or generalized coordinates. When more exactly the term parameter will be used indicating a quantity which is fixed, we will state it clearly, okay? But in general, these two terms are interchangeable. Or otherwise, we have dependent coordinates. Okay, so let's make an example. Okay, so example. Let's see if any one of you has ever seen. No, sorry. This. There you go. Do you know what this is? Has any one of you have studied this mechanism? So this is called the Poisselier mechanism. Okay, and it was typically used to do what? How does it work? So basically here you have two fixed elements, two fixed bodies, which are again, let's say attached to the ground if you want. And then you have a series of links, which basically would be simplified this way. So here you have typically an engine at point D, which exerts a torque. Here at A, you have just a fixed hinge. And all of this is made to convert a rotary motion here in a linear motion of the point P, which describes this rectilinear trajectory. Okay? It's one of the classical mechanisms. All right. So let's do some counting. What is the number of bodies here? So these also count as bodies, so these and these as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 9 bodies. Okay. That's to say that what is the number of generalized parameters that we can call n? Would be 9 times what is the number of parameters that you need to identify a body, a rigid body, in the 2D space. In the 3D space, we have said 6 or 7, depending on the parameterization that we use to identify the attitude. But in 2D space, yes, 2 displacement and 1 rotation. Okay, so it's 3. Has to say that we have 27 QS. Okay. Okay. Now let's see how many constraints do we have. Okay, so I say that here we have a fixed constraint, because here what would be the engine is fixed to the ground. So how many constraints, equations do you need to characterize a fixed constraint? So it has to limit what? All of 3 degrees of freedom. Let's say it now clearly. All 3 parameters that you need to again, identify this body here. So how many equations? 3. Okay. So this is a fixed 3, fixed. And here as well, so 3. This second body. Okay. This square body here, which you cannot really see very well, is fixed to the ground as well, so another fixed constraint. Then all others are hinges. Okay, so how many constraints do you need to define an engine? An hinge. You need to fix 2, because the 2 displacements must be limited. Only rotation is allowed. Okay, so here you have, let's, for example, denote it with a green color, 2 here, and 2 here as well, and 2 here as well. These are simple hinges. All right, but then we also have something else. Why? Because here we have these 3 hinges, but these 3 hinges, they connect 3 bodies. So how many constraints do you need here? Actually, sorry, this is 2. Oh, but this is not 2, because here, in fact, you have 3 bodies connected. Okay, here is just 2. But here is 3. Okay, so here, 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 and here you have 3 bodies connected through a hinge. So how many constraints do you think you need? No, it's not 3. Just guess. So you have to basically constrain the motion. You have to constrain the motion and allow the rotation. So here, what you have to say is the following. This body here, in its position here, must have this position coinciding with the position of this body here, of this point of the body, and this point of this third body. So these 3 points, they must be one on top of the other. They must be attached. Okay? So the position of a point is identified by 2 equations. All right? Vertical and horizontal, for example. Then so you have to say that this point on this link must have the same position of the same point, but belonging to this link. And then that this point on this link must be the same of this point of the link on the background. Do you actually need to say that this must be equal to this? No, because if this is equal to this and this is equal to this, it follows that also this is linked to this. Okay? Is it clear? No. All right, so let's say that this is body. Let's call them names. So A, let's say A star, B star, and C star. Okay? So what is point B there actually belongs to A, B, and C star. Okay, there are 3 different points originally. Okay, what you have to say is that point B belonging to A star, point B belonging to B star, and point B belonging to C star must be attached. Okay, so if you have to say that this point that B, let me write that B belonging to B star must be equal at all times of B belonging to C star. That must be equal at all times of B belonging to A star. So the position of these 3 points are basically defined by 2 equations. Okay, this is 2 coordinates, x and y, if you want. So here you have 2 equations here. This is one pair of equations. This is another pair of equations. But then what else? What else do you need? How many? Do you have to actually say that BA must be equal to this? No, because you see, the identity enforces that once you have said that this must be coincident with this, and this must be coincident with this, it follows that A star and B star also have to enforce the same thing. So this is, again, a hinge. You said it. This is a hinge. So 4 equations. Okay, 4 equations. It's not a simple hinge. It's a double hinge because it's connecting 3 bodies. While typically a hinge, the most simple hinge, connects only 2 bodies. Okay, so let's write it. So here we have 4. Here we have 4. Here we have 4. And here we have 4 as well. Okay? So each one of these complex, if you want, hinges is characterized by 4 equations. So if you sum this up, we have 16 equations coming from, let's say, these complex hinges, because there are 4. Then we have 2 simple hinges. They amount to additional 4 equations. And then we have 2 fixed constraints amounting to 6. So 16 plus 4 plus 6, we have 26 constraints equations. Let me add one very, very, very important word: independent constraint. Independent constraints equation. What does it mean, independent? Linearly independent. It means that each one of these 26 equations cannot be obtained through a linear combinations of the others. Okay? For example, here, when we said that the point B of A star must be the same of point B of B star, and must be the same of point B of C star, we said 4 equations, because we didn't have the need to also say that point B of C star must be equal to A star. Let me just rewrite it. So here we have that point B of A star must be identical to point B of B star. Then we had that point B of C star must be equal to point B of B star. Now, these are the 2 equations that we wrote for the complex hinge. And then we said, you don't actually need to write that also point B of A star must be equal to point B of C star, because it follows from the first two. Okay? When I say it follows, it means that this is a dependent. Actually, there are two. These are two constraint equations which are linearly dependent from the previous two. What does it mean? It means that you can obtain these two through a linear combination of this. Linear combination means through multiplication and addition of the terms of this. Okay? So this, when you do the counting here, you have to count only the constraints equations which are independent. Okay? Linearly independent. Okay? So, what is the number? Let me cancel this out. So what is the number of independent parameters? N ind is basically MB, so it's N minus, so the total number of the parameters, minus the constraints, linearly independent constraints. That's to say, 1. Okay, so of all the mess that this mechanism is, you can only set one parameter freely, and just setting that parameter will univocally identify the configuration of the mechanism. All of the rest will follow through the constraints. Okay? If you think about it, it makes sense. Why? Because if you, for example, if you want to drive this mechanism as it is typically used for as a transmutation, as a transformation between a rotary motion and an axial motion, you identify an angle here, an angle of this body, and automatically you will get a position of the point P. You see? So that's one parameter, namely the orientation, and all the rest is set, is defined. On the other way around, you can either use this also to convert axial motion to rotary motion. So if you set a position of point P, you will get an angle here at point D. Okay? This number of independent parameters are called degrees of freedom of the system. Okay? Typically abbreviated with the acronym DOFs. Degrees of freedom. Okay. Now, depending on the number of degrees of freedom, we can typically discriminate a structure and a mechanism as well into 3 different categories that you have already seen multiple times. So, if the degrees of freedom of one system is 0, what does it mean? It means that it's completely constrained, it cannot go anywhere, rigidly. In that case, you have a so-called isostatic structure. Isostatic. Structures are typically wanted to be isostatic. Okay, so civil engineers they do want to build structures which do not move rigidly, typically, no? So they want to have isostatic structures. But mechanical engineer, typically when they build mechanism, they want them to possess the possibility to move. That's why they want an n which is higher than 0, larger than 0. And these mechanism and structure are called labili, labiles, okay? Strutture labili. When instead the number of degrees of freedom is negative, meaning that you have more constraints than actual possible parameters that you need to describe the motion, the configuration of the system, you have an, what is it called? Hyperstatic structure. And this is also something typically that characterizes structures designed by civil engineers. Okay? So let's write it. So depending on n, on the number of degrees of freedoms, we can have n independent equal to 0, and then we have, as I said, isostatic. Confusione. Then we have number of independent parameters larger than 0, and we have labile systems. Sorry. Ragazzi, noi stiamo facendo lezione, dovete fare silenzio, che non si sente niente. Grazie. Ok. Smaller than 0, we have hyperstatic structures. Okay? So this is a classification of the system in terms of the number of independent parameters that you can set. But there is also a classification of the constraints. And we'll start to introduce it here, but we'll see it more truly in the next lecture. And it's the distinction between, which I think I already mentioned, between holonomic and non-holonomic constraints. So from an intuitive point of view, what's the difference? Holonomic constraints, they typically limit, they constrain the configuration of the system, so the positions, configuration. Non-holonomic constraints typically constrain the motion of the system. Examples. So a hinge, it's a, no, it's a holonomic constraint. He said non-holonomic. Holonomic constraints. A ball which rolls on the floor without slipping. So it rolls without slipping. Already, if you think about the definition, it should guide you. Is it holonomic or non-holonomic? Non-holonomic. Because it constrains the way it moves. It must roll without slipping. Okay? Without sliding. And that is a non-holonomic constraint. Okay? We'll see that apart from this intuitive definition, there is a more deep, more pregnant physical meaning and mathematical meaning behind, this classification. And we will also see later on in the course that these equations, the constraints equation, will have to be phased. You have to take into account them while studying the motion of the system. So you have the equations of motion, and then on one side you also have constraints, equations of the system. So the system must move, always respecting the constraints equation, okay? And for constraints equation of a certain type, namely holonomic, it is possible to include them directly in the equation of motion through a particular formulation, which is Lagrange formulation. We already said it. So Lagrange, the real advantage of Lagrange treatment for the motion, for description of motion, is that it allows to include directly the constraint equation within your equation of motion. So you forget about them, typically. With non-holonomic equation, this is not possible. And they will need another care to be treated, okay? But we will see it, next time.